Okay, next term, duty cycle. So the duty cycle, just like when we had for eStim, right? It was the on and off time. So we were able to manipulate that for our muscle re-ed and have the time that the wave was on and then the time that the wave was off. We can do the same thing with ultrasound for a different reason in this case. So it's the percentage of time the ultrasound energy is being emitted from the sound head. So if you have a 100% duty cycle, then 100, the entire treatment time energy is going through the beam. And so we're going to be producing a lot of energy in the body with a 100% duty cycle. So we tend to use that more when we're talking about thermal effects. If we set a lower duty cycle, so 50%, 25%, 20%, the idea being that we are now increasing the amount of off time, which means that the body can dissipate whatever heat we might produce fairly easily. We then are trying to maximize the non-thermal effects while trying to minimize the thermal effects. Okay, so pretty much whenever we're setting a duty cycle, it's because we're trying to get non-thermal effects versus thermal effects. So again, continuous, the ultrasound intensity remains constant over time. So we see that here where we constantly have this then tissue temperature increase happening. So again, usually used for thermal. Pulsed, we're going to interrupt that average intensity of the output over time. And so then the intensity gets lower. So if we have a 25% duty cycle on, this is what this indicates, that 25% of the time the beam's actually up. And so the intermuscular temperature can never actually increase because the body has time to take blood flow and put that away. It doesn't have the molecular energy needed to keep steadily rising with the increase of temperature. So the body can compensate so we don't get any heating. So the duty cycle, or sometimes called the Mark-Space ratio, okay, is the duration of the pulse divided by the pulse period. And then we times that by 100. That's how we get the percentage. Okay, so it's essentially this idea of how long is the pulse on versus how long is the entire pulse period. Okay, so again, usually primarily non-thermal. We can target both superficial and deep with either pulsed or continuous ultrasound. So we can use our 3 megahertz or our 1 megahertz. Okay. We just also want to remember that if we are using continuous, especially, we got to keep in mind our BNR, right? We don't want that to exceed 8 watts per centimeter squared. And so, if we're using 100% and the machine is always producing energy, we're more concerned about that beam profile and those peaks that we might be producing. Okay. The lower the duty cycle, we have that chance for any heat to dissipate. And so most of our peak or these average spatial intensities that we're going to be talking about that we want for the pulsed ultrasound, the idea being that if we can keep that intensity below 0.2 to 0.3, okay, somewhere in that range. So this is, again, thinking about the total treatment over time. So the output that we're reaching when the machine is on, plus taking into account the off time. So by multiplying by that percentage, right? If we keep that to 0.3 to 0.2, we're gonna keep it to the point that we don't actually get tissue temperature increase. So usually the less chance to heat the tissue with the pulsed with non-thermal. So we tend to use it that way. So when we look at the equation later, when we start talking about actually setting up these parameters, we're always going to want to try to keep that average spatial intensity and taking into account the off time at about 0.2 to 0.3.